In this video, we're going to look at question 4 from page 43, I think, of the course notes. And we're not given a diagram in this question, so we have to start to piece together the information ourselves. But let's start off with what we're told of the cross-section. We're told the cross-section of our beam here is 0.25 meters deep and 0.12 meters wide. Now, we could convert this into millimeters quite easily, but sometimes questions give us a wee clue about what we're to do with it. So as long as we are consistent with your calculations, all lengths in meters, or they're all in millimeters, we're going to be fine here. We're also told we've got a simply supported beam. So that means a beam that's supported at either end, not the best straight line in the world, but there we go. And that the length of this beam is 10 meters. We're told we'll be looking for a load that can be carried at mid-span, which means halfway along the beam. And we're also told the maximum allowable bending stress is 100 meganewtons per meter squared. This is all the information we're given in the question. But that's actually quite a lot to be going on. We're asked to find this load here and what's the maximum load that can be carried at the midpoint if we don't want to exceed this maximum bending stress of 100 meganewtons per meter squared. So the first question we might ask is, if our formula is got stress, bending moment, our y value distance from the neutral axis and I, where do we get the load from? Well, where we get the load from in this question is the fact that our beam is a standard case. I'll bring this image in from the course notes. We have this scenario here, scenario 1 from page 19. We've got a simply supported beam with 1 point load at mid-span. So from this, we can take this formula here, that the maximum bending moment is going to be given by the UDL times the length divided by 4. So I'll get rid of this image now, but we'll make a note of this formula here. M is equal to WL divided by 4. So what does this mean for this question? Well, what it means is we've been given L. We know what L is, it's 10 meters. So it means that if we can find M, then we can calculate W. So we've got a formula for that. So that's what we're going to do here. So let's get some other values we can read off quickly. Well, if our centroid line is the halfway point in a rectangle, the Y value, the distance from the centroid, the furthest away piece of material is here. So our Y value is going to be half of our 0.25 meters. So our Y value is going to be 0.125 meters. Then the only thing left to do is to work out our bending moment, our second moment of area, not a bending, we'll come to that in a second, our second moment of area about the XX axis. So we just use our standard formula for a rectangle. So we've got BD cubed over 12. Now, we're keeping our values in meters. And what that means here, rather than having millimeters to the power 4, these have units of meters to the power 4. So let's put in our values. We've got 0.12 for our B value, 0.25 cubed for our D value, and 12 for our just the constant at the bottom of the equation. This is going to give us something very small. It's going to give us something with a negative coefficient, a negative power for our scientific notation. So what we have here is 1.5625 times 10 to the minus 4 meters to the power 4. So that's 0.0001565. That's the number that we get out here. And that's entirely normal because we're working in meters to the power 4 rather than millimeters to the power 4. But that gives us our second moment of area. So let's see what we've got. Well, we've got a value for maximum stress, a value for Y, and a value for I. So we can use all three of these to calculate M. So we'll rearrange our formula from stress to the bending moment. So M is equal to stress times second moment of area divided by this distance, and then put in our numbers. So we have 100 times 1.5625 times 10 to the minus 4 divided by our value for Y, which we found was 0.125. Now let's think, what are our units going to be when we come out here? Well, all of our distances are in meters, so our answer is going to be in something per meter squared. We're using meters to be something meters, not per meter, for example, bending moment. So we've got meters squared here, we've got meters for our y value, and we've got meters to the power 4 for our second moment of area. So it's going to be meters. Now, the only other unit we're using is a force unit, and it only comes for a stress. It's going to be meganewtons. So our answer here is going to be in meganewton meters, and we just need to check we're being consistent with our units. So we put all of this into the calculator. So 100 times 1.5625 times 10 to the minus 4. Divide that by 0.125, and we get an answer of 0.125 meganewton. That comes from the stress, meganewton meters. And we need to remember that so that we're keeping our units consistent. Then lastly, how do we get this value W? Well, we take that formula that we have for what maximum bending is equal to from our standard case. So just shift down to get a bit more space. So we can say M is equal to WL divided by 4. We've worked out our value for M, 0.125. W is what we're trying to find. Our length of our beam is 10 meters, so let's put that in, and that's divided by 4. So we can rearrange that. W is equal to 4 times 0.125 divided by 10, which is equal to, quickly do that. I was going to say what it was, but I think I'll work out just in case. Is equal to 0.05 meganewtons, or you put that more simply, that's the same as 50 kilonewtons, because there is 1,000 kilonewtons in a meganewton. So multiply that by 1,000, we convert it to kilonewtons. So 50 kilonewtons is the answer there. So a few more extra steps to consider compared to some other questions, but using those standard cases in page 19, we can make anything when we're working with the maximum bending moment a bit simpler.